Hello and welcome to a new video on cryptography for everybody in the Basics of Cryptology series. In today's video, we will have a look at modes of operations of block ciphers. I structured this video into 6 different parts. In the first part, we will see what a block cipher mode of operation actually is and why we need this. Then we will have a look at different modes, namely electronic codebook mode, cipher blockchaining mode, cipher feedback mode, and output feedback mode. After that, we will have a look at some more modes, which we will not discuss in detail in this video, but possibly in one of the next videos. And after that, of course, we will have a look at the different modes in Cryptool 2. And as you can see here, in this light gray, we have the next topic of the Basics of Cryptology series, which is padding of blocks of block ciphers. But before we start, we will have a look at this graph here, which you will probably remember from the last videos of the series. And as we know, cryptography is the art of making ciphers and cryptanalysis is the art of breaking ciphers. And the video today deals with cryptology, cryptography, modern cryptography, and symmetric modern cryptography. What is a block cipher mode of operation? First of all, let's remember what is a block cipher. A block cipher encrypts blocks of data of the same size. For instance, AES works with 16-byte blocks and the DES works with 8-byte blocks. So the plaintext that goes into the cipher here has the block size bytes plaintext, so for instance 16 bytes for AES. Then of course we have the key that goes into our block cipher, and then we get as an output the block size bytes ciphertext. So the block cipher always encrypts one block of data, and of course when we want to decrypt using the block cipher, we put in this block size bytes ciphertext, and then as a result, of course with the correct key, we get block size bytes plaintext after decryption. The problem now here is how to encrypt plaintexts which are longer than the block size. Usually data you want to encrypt has not only a length of 16 bytes or 8 bytes, we want to encrypt several hundreds or thousands or maybe even millions of bytes. And the solution to that problem for block ciphers are the block cipher modes of operation. And what these are, we will see on the next slides. And here we have our first mode, which is called the electronic codebook mode, or in short abbreviated the ECB mode. And this mode encrypts each block independently. So when we have more than the block size data, then we divide our data into the blocks that the block cipher can then encrypt. And for instance, we have the first block here and the second block here and the third block here. And we use the block cipher individually on each of these blocks. So we get the first ciphertext block, the second ciphertext block, and the third ciphertext block. Clearly, for each block, we use the same key. Now, how do we decrypt then these blocks? We just use the same block cipher, of course, with the same key. And then for the first ciphertext block, we decrypt, getting our first plaintext block back. Then for the second ciphertext block, we do the same. And for the third ciphertext block, we do the same. So each block is encrypted and decrypted independently. Now with this mode, we have a problem. And the problem is that same plaintext blocks are encrypted to same ciphertext blocks. In the later part of this video, we will also see why this is a really bad problem, because this leaks data, as we will see later. And therefore, the electronic codebook mode is deprecated. And you should never ever use electronic codebook mode in any application. This is a flawed block mode, and this is only here in this video to show you that you should not use it. And sadly, many even modern libraries still support the electronic codebook mode for encryption. Now let's have a look at a better operation mode, and that is the cipher blockchaining mode, or short CBC. And the basic idea of the CBC mode is that it chains all of the plaintext blocks, as we can see here. So our first plaintext block goes into the block cipher, but it's XORed with a so-called initialization vector, or IV abbreviated. And this IV is public knowledge, so this is not secret as the key. And this IV, for instance, is also sent to the receiver that he can use the IV also for decryption. The basic idea of the IV is that when you have different IVs, but you encrypt the same data, then the ciphertext, the resulting ciphertext is also different. Why is this resulting ciphertext different? Since the IV is used to change the plaintext. And then in the cipher block chaining mode, the ciphertext is fed back to the next block. So we use the second plaintext block, we XOR it with the previous ciphertext block, and then encrypt this here. And then we do with the same with the third plaintext block. It's also XORed with the previous ciphertext block, and so on and so forth. This is why it's called cipher block chaining. All cipher blocks are chained. And a single change, for instance, in the plaintext or in the IV, leads to a change in all of the following blocks. And this is a nice property of this mode, so that every time, even when we encrypt the same plaintext, but we change the init vector, that it changes all the ciphertext. So no data leaks anymore. And also same plaintext blocks are encrypted differently because these are also chained. And of course, decryption works the other way around. So we take our first ciphertext, we decrypt it, and then of course we have to XOR it with the init vector so that we get back our plaintext. Then the ciphertext is also given to the next block or used with the next block. So the next block is decrypted using the block cipher, and then it's XORed with the previous ciphertext to obtain our plaintext. So as I said, the cipher block chaining mode XORs the previous ciphertext block with current plaintext block. It solves the problem that same plaintext blocks are encrypted to same ciphertext blocks. And changing one bit in a plaintext block or in the IV changes all following ciphertext blocks. But unfortunately, there are also attacks on the CBC mode. For example, an attacker can modify every second plaintext block if he knows the complete plaintext. This attack we will also see in the later part of this video where we use Crypto2. Now let's have a look at the so-called cipher feedback mode, the CFB mode. And this also chains all blocks. As you can see here, we have an initialization vector, and this is encrypted using the block cipher, for instance, the AES or the DES, using our key. And then we get a block of ciphertext as an output of the block cipher, and this block is then XORed with the plaintext. Then the ciphertext, the resulting ciphertext block, is used as an input for the block cipher, and the output of the block cipher then is XORed with the next plaintext block to obtain the next ciphertext block. And this is repeated until all of the plaintext blocks are encrypted. And to decrypt, we use the initialization vector again. We encrypt this using the block cipher. Then we get our plaintext, and our ciphertext of the next block is then XORed to obtain our plaintext. This ciphertext then is used also as input for the next block. The key then is used to encrypt the ciphertext of the previous block, and this is then used again to decrypt the next ciphertext block with XOR to get our plaintext. And this is repeated and repeated and repeated until we deciphered the complete ciphertext. And basically, this mode uses the block cipher to generate random bytes. So these bytes that here come out are like random bytes, which are XORed with the plaintext block. And this basically generates a key stream using the block cipher. So basically, this mode turns the block cipher into a stream cipher. Now let's have a look at the final mode. And this is the output feedback mode, or short OFB. And this also chains all blocks. And it basically behaves like the mode before. But as you can see here, in this part of the diagram here, there's a small change. Because instead of using the final ciphertext as input for the next block, it uses the block cipher output as input for the next block. So we first encrypt the IV, then get the output as a kind of key stream that we XOR with the plaintext to obtain the ciphertext, but the output of the block cipher goes into the next block cipher round for the next block, and we repeat this again and again. And of course, for decryption, we do the same. We use the init vector that goes into our block cipher. We get out our, you can say, key stream to decrypt the first ciphertext block. Then this output is also used for the block cipher again to produce the next bytes for the decryption. Then it's XORed with the ciphertext to get the plaintext, and so on and so forth until we deciphered all the blocks. And as I said, this mode also uses the block cipher to generate random bytes, you can say, which are XORed with plaintext blocks. And this basically generates a key stream using the block cipher. And yeah, this turns the block cipher also into a kind of stream cipher. Now I have some more modes of operation that are not part of this video, but I want to still name these here. And we so far covered in this video the electronic codebook mode, the CBC, the CFB, and the OFB. And other modes are, for instance, the CTR mode or counter mode. And this uses a counter to generate also a stream cipher. So basically you have a counter, and this counter, or the value of the counter, is then encrypted, and the resulting ciphertext is used for the current plaintext block for the encryption, or for the current ciphertext block for decryption. Then we have the XTS, or exec-based tweaked codebook mode with ciphertext stealing, and this uses a so-called ciphertext stealing technique, and this mode is especially used for hard drive encryption. But today, block modes of operation also support authentication of data, and then we speak of authenticated encryption with associated data, or abbreviated AEAD modes. And some examples are, for instance, the CCM mode, which is the counter with CBC MAC, and this is an authenticated encryption mode, and it provides authentication and confidentiality. This is one mode that we probably will cover in a future video. And then we have the GCM, or Galois counter mode. And this is also an authenticated encryption using Galois message authentication code, or GMAC. And this mode is also probably covered in one of my future videos. Now that we had a look at 4 different modes, let's have a look at block cipher modes of operation in Crypto2. And as I said, I want to also have a look at 2 different attacks or flaws of 2 of these modes. I'm here now in the start center of Crypto2, and at first I want to show you different operation modes for block ciphers. And I will use the AES cipher. So I search for AES here, and I want to use the AES cipher with text input. So let's zoom out a little. And I think it would make sense to put me on the right side here. So what do we have here? We have here an AES cipher, and you have the settings of the AES cipher here. And here you have different modes. For instance, the electronic codebook mode, the cipher block chaining mode, the cipher feedback mode, the output feedback, and we have the EAX mode that we did not cover in, or do not cover in this video here. And I think it makes more sense to change this to hexadecimal, and then we want 16 bytes as input, so 1. And then we have here the encryption. This is our key. I think, let's change the font here. And also the font here. And now let's first encrypt using the electronic codebook mode. And we also change this here. Okay. I think 20. Good. Now you don't see anything because this is just AES encrypted. But the interesting part is when we want to encrypt more than the block size. So let's encrypt 2 blocks. And I just choose 2 same blocks. So we have all set to 0 here. And when I encrypt using the electronic codebook mode, we will see that I think it makes more sense to use Courier here. We should see that these 2 blocks are encrypted the same way. 16, and then we have a second block here that goes to here. And since I have chosen a padding, that's part of the next video, let's just remove it. And here we can see that our cipher encrypts, or that this mode encrypts 2 times the same block to the same ciphertext block. And this is really bad. And that we will see later when we have a look at the flaws of these modes. Now let's change the mode to cipher block chaining. Remember, then these two blocks are still the same, but these are chained. And when I now press play, the first block, of course, is encrypted the same. The initialization vector that should be used here right now is also set to 0. That's why our first block here is the same. This is the same cipher blocks as before. But since these blocks are now chained, you can see that the second block here is different because there's a feedback going from the first block to the second block in the cipher block chaining mode, and this leads to a change here. Now let's have a look when we go back to the ECB and we change a single bit. So I just change this to 1, and then only the first block here changes. The second block remains the same because these are not chained. So let's revert this. And when we go to cipher block chaining, again, let's change the first byte here. And as you can see, all the bytes after this, so the second block also changes because these are chained. And when we change only a single bit in the input here, all remaining or all following bytes also change. Let's have a look again at the electronic codebook mode and see what happens when we change an input 1 bit of the key here. So I change only 1 bit here from 8 to 9, and then everything changes, but still, since we have electronic codebook mode, these 2 blocks are the same. Let's have a look how it behaves when we change to cipher block chaining. So we have 2 different blocks here, and when we change 1 bit of the key, like for instance here again, then also both blocks change and they are still different. Now let's have a look at the other modes, for instance the cipher feedback. So we have here also 2 different blocks as output, the first block and the second block. But what happens when we change, for instance, only a single bit in our input? Then you can see that here the first byte changes and the remaining bytes also change. And what happens when we change the key with the CFB mode? Then also all the bytes change here. Now let's have a look at the output feedback. Remember, this is also a mode that turns our block cipher into a stream cipher. And when we change here a single bit, in this mode, and this is a drawback or a flaw of this mode, only the byte at the position here changes where I change the byte. Here is the same. Here I had 20 and now I change it back. You can see with the OFB mode, like with any stream cipher here, when I change a single bit in the input, only a single bit in the output, or yeah, the single bit in the output changes. Of course, when I change the key here, for instance to F here, then all the bytes or bits here change. But in the input, and this is the flaw of this mode also, only a change of a single bit in the output. So the output feedback mode is also not a good idea, because it does not change as much as we would like it to change. Now let's have a look at some flaws. Why shouldn't we use the electronic codebook mode, and why should we use the Cipher block chaining? And for that we have a nice template here, and that's called Block Modes of Symmetric Ciphers, or CBC. So what do we have here? We have here a picture, which is a smiley. That's called plaintext smiley. And we have 2 times the AES, so a very strong cipher, 1 time with the electronic codebook mode, and 1 time with the Cipher block chaining mode. And every time we start this workspace here, a random key is generated. Both ciphers use the same key, but different modes of operation. Let's see what happens. Here we have our plaintext smiley. So we can clearly see, of course, this here is a smiley. On the right side, we have encrypted with the electronic codebook mode. And as you can see, we have some data leakage here, because same plaintext blocks are encrypted to same ciphertext blocks. So the general structure of that smiley here we can see. So we still can see that this is a smiley. And this is really bad, because, yeah, as I said, it leaks data. And here, with the Cipher block chaining mode, this just looks like white noise or random noise. And this is exactly what we want to have. We don't want to have any data that leaks out of this encryption here. So this is why you should always or never use electronic codebook mode, and prefer to use the Cipher block chaining mode. But we will now also see why the Cipher block chaining mode is not the best mode to use, and you should use more modern modes. Let's have a look at the CBC attack template here. Okay, so what do we have here? Okay, what can we see here? Let's imagine we want to send an invitation list for a birthday party, and we have different names like Hannah, Emily, Niklas, Simone, Thomas, and so on. And we want to send this list to someone who prepares the invitations. And we, of course, don't want anyone to know who we invite to our party, so we encrypt this using the AES. Now let's think of an attacker who knows this list. And since we use the Cipher block chaining mode here, he can use or to modify the array or the data that we send to the receiver. And as you can see here, with some clever chosen bytes that we XOR on the ciphertext, since we know the plaintext, and remember the Cipher block chaining mode changed the ciphertext blocks, we can manipulate the list. And we can manipulate it in a way that every second entry is changed. So in our second entry here, we have Emily, but here we have Sophia. Then in the 4th place, we have Simone, but here we have now Moritz. And we changed Julius to Melina and Niklas to Fabian. And we could do this because we knew the names here. So we prepared this modify ciphertext array here that is just XORed on the ciphertext. And then on the receiver side, you will only see these names here. Clearly, you can see that here is some corrupted data. But let's imagine someone who just needs the names and thinks, okay, there's a problem, but I can still read the names. And now he invites the wrong people to our party. And you would now say this is some kind of constructed attack. And I would agree, yeah, this looks like a constructed one. But the problem is that this technique here that is used to modify the list using the CBC attack was used to attack the disk encryption of Linux, the LUX encryption or LUX partitions. And here on the right side, I'm probably in the way, but here you can see Here's an article. If you're interested, you can go to this article. I think I will also link this below the video. And in this article, you can see how these modifications, this possibility of modifying cipher block chaining encrypted texts to actually attack the Linux file encryption. And this went so far that people could inject malicious code into the partitions that is then executed when the partition was decrypted, and then the attacker had access to that Linux machine. And that's why they didn't use cipher block chaining then after that point anymore. So cipher block chaining should always be used together with some integrity checks so that you can see when the data is modified. Yeah, and this is the last attack that I wanted to show you in this video. I think you now know how the 4 basic modes of operation of block ciphers work, and that even the standard ECB should never be used anymore, and why. And that the cipher block chaining mode has also some flaws, as I have shown you here. And yeah, this is everything I wanted to show you in this video. As I already said, in one of the next videos, we will have a look at padding. So how can we encrypt blocks that are no full blocks, so only parts of blocks that are not full blocks of the cipher we want to use. And yeah, this is everything I wanted to show you. I hope you like it. If yes, please give a thumbs up. Also, if you did not yet subscribe to this channel, please do so. This really helps me to grow the channel and to make Crypto 2 more popular. Also hit the notification icon if you want to know when I upload new videos. So thank you very much for watching, and see you in the next video.